Welcome. This is the second of the two expansion equations I wanted to talk to you guys about today. And this one is what I call the no-time motion formula, or no-time motion equation. Uh, you'll see why in just a minute. I think it might be pretty obvious to you. So I call it, like I said, no-time motion equation. No big deal. There it is. I want you to take a look at this equation here and tell me where time is located in that equation. Easy. It's not, right? So no big deal. That's why I call it the no time motion equation. So here's the question. When would you actually use this? Well, there are a number of problems that you'll get that are motion based that will, instead of giving you a time to work with, they'll give you a displacement. So this delta x right here is your displacement. Now you could replace it with a height or a delta y or d if you want for distance, whatever makes you happy. This right here is your acceleration, so it's assuming that the situation is one in which the speed is changing. Here you have a squared, so don't forget that, but it's an initial velocity, so that's an instantaneous velocity right there. It's how fast it's going right at the moment you start watching. And then here you have your final velocity. And typically what you're going to be asked is, can you tell me how fast it's going right at the end? And so that's your v sub 2 right there. Now notice for both of these, you've got a v squared and a v squared. Crucial, 95% of the time you get a problem wrong using this, it's because you didn't square one of those two or both. And so you don't want to do that. You don't want to fall into that trap there. So please don't. It's pretty easy to do, so be careful. One of those that I can, sometimes I even get into trouble with it. So here's a situation in which you might use this. So let's say I have a ball that is sitting on a cliff. There's the ball. Okay, there's the cliff, and the ball is, let's say, 30 meters above the floor of the cliff, the bottom of the cliff there. Okay, 30 meters. So here you would agree, if it's sitting on the cliff, that its initial velocity is 0. And so if you're smart, you'll always try to pick a situation in which the initial velocity will be 0 while you're doing your experiments. Because then, of course, this term drops out. That's great if you can do that. So my question for you is, if this ball falls off the cliff, how fast is it going right when it hits the ground, just before it hits the ground? So I will never ask you, of course, how fast is it going after it hits the ground, because that's dumb, right? It's going 0, assuming it stays intact. But here's the question. As it's moving downward, what's actually happening to it? And I think you'd agree that initially it has a small speed, and then it increases its speed, and it increases its speed as it falls until finally it has its largest speed right there, right before it hits the ground. How much is that? Well, let's see if we can figure it out here. I'm just going to get rid of these. Whoops. Didn't want to get rid of that. I'll have to draw that again here. There we go. And so here's my question. What's v sub 2? Okay, so first off, I want to try to make sure that v sub 2 is isolated. And so v sub 2 squared is a bit of an issue. So what I'm going to do is take the square root of both sides. I remember that this term is going to drop out because I chose to have a problem in which the initial speed was 0. So v2 squared square root is equal to the square root of 2a delta x. Now I'm going to change this because here is technically a delta y, right, or a height, because it's a vertical displacement, and a is technically g because what's causing this to fall? Well, it's acceleration due to gravity, which is negative 9.81 meters per second, and so that technically is g. So as I rewrite this, it ends up being v sub 2 is equal to the square root of 2 little g delta y, which is also on your formula sheet. So you might want to just check that out here. I think this formula is 2.5 on the sheet. Oops. And the other formula is like 2.7, if I recall. This one down here is like 2.6 or 2.7. So if I wanted to solve this here, how could I do it? Easy enough. How far does it fall? 30 meters. How much does it accelerate? Negative 9.8 meters per 9.81, sorry, meters per second. And you immediately see that you run into a problem, because 2 times negative 9.81 times 30 is going to give you a negative answer, and then you try to take the square root, and now we're into imaginary number land, and you don't want that. You have to remember that it starts here and moves its way downward, and so technically this is a negative 30 meters per second, or meters, excuse me. So that negative and this negative, when you multiply them together, ends up canceling out. And so we have the square root then of 2 times negative 9.81 times negative 30, like so. And then I'm going to do this not in my head, because it is too hard for me on a Sunday afternoon. I don't know. Times 9.81. And then the square root of that gives us a speed of 24.261 meters per second, because it's a speed velocity, right? Now, technically, you would know, we would have to remember that this is in the negative direction here. So, because it's moving downward. Just keep that in mind. Even though this is giving us a speed, you want to make sure to answer in a velocity, right? So you need a direction there. So 24.261 is too many sig figs. I have 3 sig figs here. This doesn't count for sig figs. And I don't have anything else in the problem, so 3 sig figs is my answer. So there it is right there. Negative 24.3 meters per second, rounded off. Hope that helps. Let me know if I can answer any questions. Thanks.